Okay. Good morning, everyone. I think we're about ready to get going, if that's okay. So it's a great honour this morning to introduce this morning's speaker, who is Martin Siegert. Martin has a PhD in numerical modelling from Cambridge University. He's currently a professor of geosciences and the co-director of the Grantham Institute of the Imperial College London. He was previously the director of Bristol Glaciology Centre at the University of Bristol in the UK, and previously the head of the School of Geosciences at the University of Edinburgh. And before that, he spent some time at Aberystwyth University. Martin, of course, has conducted many important field expeditions, authored many important papers, and is a recipient of multiple prestigious awards, including he's a fellow of the Royal Society in the UK. With that said, I hate to give long introductions, so if I could hand off to you at this point, Martin, that would be great. Thank you so much again.
Thank you ever so much. And listen, thank you ever so much for inviting me to this lecture series that you're having. I've just been amazed by how many people that you've had speaking in your sea level series. It's just been phenomenal to see all the emails come through and all the people that are speaking. And I wonder what I can contribute that you wouldn't have already heard, actually. So I was thinking I'd speak about something slightly different today. And I sort of dug up a presentation I did a little while ago and added a few extra things to it to see if we can make it relevant. But I guess one of the reasons I was asked to, well, this is me in West Antarctica a few years ago with a Russian Ilyushin IL-76 behind me, which is an amazing aircraft landing into the Patriot Hills. All good. I mean, obviously, this is what you would have heard about before, and sea levels going up globally. 20 centimeters since the 1870s or so. Wonderful measurements from the tide gauges, and very recently from satellite data. It's going up, and it's going up at increasing rates. This is the sort of stuff that you know about, of course. This is from the World Meteorological Organization's State of the Earth assessment just a few months ago, to say that 10 centimeters of sea level equivalent have gone up in the last 30 years. Also with increasing precision, and again the rate of change is going upwards, and we know that half of this is of course caused by thermal expansion, but increasing numbers of sea level rises being caused by melting of glaciers and of the ice sheets. And glaciers and ice sheets now contribute more than thermal expansion, by the way, and that's not going to be reversed. That's just only going to continue into the future. So when you look at the contributors work that was done at Leeds a few months ago, when you look at the contributions of the Antarctic and Greenland ice sheets, and we can compare those to the fifth assessment report projections of what they might be doing under the various scenarios, you see they track along the worst case scenario of warming. And that's really concerning for us, because the Antarctic and Greenland are massive stores of ice. And if they start to get mobilized and start melting, then there is significant sea level consequences for the world. Everyone here will know about that. And this is what we're worried about, the Antarctic ice sheet. It's the satellite observations of change in specific regions that give us great reasons to be concerned about in West Antarctica and in bits of East Antarctica, in both cases where there are, the ice is resting on a bed that's way below sea level. And so you have this marine ice sheet instability hypothesis can start to kick in and get runaway effects. So this won't be of news to people on here, and I don't propose to go into details about this sort of stuff, other than to say I and a few other authors did a review at the end of last year on thinking about how the IPCC is dealing with this issue, and sort of containing the problem, in our opinion, a little bit too carefully, and that we really don't know. In a situation where we have very strong warming outcomes by the end of this century, what it really means for global sea levels. And what we pointed out is just a few things, that there is great uncertainty in our understanding of the response of the big polar ice sheets, and we need to understand them better to reduce uncertainties. And we came up with a list of ideas which really need to be executed in the last decade or so to help us better understand the function and flow of the big polar ice sheets, to be able to model them better. And if we can do that, our projections of how they might behave in future will be improved as well. And we came up with 6 different ideas as to well, what to do, and they're all listed here. Mapping the subglacial topography, collection of ocean data, geophysical measurements of the ice sheet base, improved coupling between models, lab field modeling investigations of fracturing, and understanding what's happened in the past much better than we do at the moment to train our models. So this, again, shouldn't be news, but these are the sort of themes that we really, really need to investigate. And some of them are obvious. We need to do better measurements in some places. Antarctica and the Greenland ice sheet, they're some of the least explored parts of our planet. And yet our models are relying on data from them to guide them to give good results that's going to influence the way that we live on the planet. So, it's difficult to see how it could be more fundamental, and yet there are still missing data gaps. So rather than just go through all this in a bit of an alarmist way, what I thought I might do is take you through some of the research that I do, which is all about geophysics, and it's all about peering through the ice to understand what's underneath the big ice sheets, with a primary reason, I guess, to understand subglacial topography, and meeting that first bullet point, by the way, and on improving models by getting a much better depiction of the subglacial bed, but other things as well that can come about. And rather than just sort of explain that in a gross way, what I thought I'd do is I would go through some history with you. And the reason I want to do that is because I think you would have heard a lot about the scientific things I would say anyway, but sometimes it's always good to understand sort of the historical lineage of why we're doing the work we're doing, how it's come about that we're doing it. And so that's what I like to do today, is just take you backwards into history and find out a little bit about why we know what we know, where that knowledge has come from, and just to really iterate the point that there's very little new in science, and a lot of the things that we're doing were first thought about by many other people that came before us, and we're still sort of filling gaps that were laid out for us by people that were doing research on this decades ago. So I just want to make that point. This is South Pole, of course. I'm going to take you backwards into history, and this stuff is all relevant today, but I'm going to explain a little bit later on. We're going to construct 3 different ages of discovery of Antarctica, if you will. The first is essentially the age of discovery, trying to identify where it is. The first person who could possibly claim to have got at or near to the Antarctic continent was James Cook. He went round the world, circumnavigated 3 times. On his second voyage, that's the one in green on HMS Resolution, he twice went southwards of 70 degrees south, and almost certainly got close, that possibly could have seen the continent itself. In fact, in the ship's log, there is a quote, which I'll read out here: "A tract of land at the pole that is the source of all the ice that is spread over this vast southern ocean." And they even refer to very strange cloud formations on the horizon, which could well be a spotting of the land itself. They got very close, but they didn't spot the land. They hypothesized it was there, but they actually didn't see Antarctica. Oh, that's the HMS Resolution, beautiful ship. Antarctica actually wasn't discovered until 1820, 1821 by 3 parties independently. So that's 200 years ago, the discovery of the Antarctic continent by 3 people. There was the Russian/Estonian explorer Van Bellingshausen. There were the English sailors Edward Bransfield and William Smith. Actually, shouldn't say that. Bransfield was Irish, never mind. And the US sealer Nathaniel Palmer, and all of them were exploiting, looking for going further and further south with an aim to identifying where the seals were. These were people who were looking at marine resources in Antarctica and economic benefits that it might do, not necessarily just for exploration itself. Really, the first scientific expedition to Antarctica was James Clark Ross in 1839 and 1843 in 2 ships, HMS Erebus and Terra. They're now sunk. It was John Franklin that took them a few years later to find the Northwest Passage, and the whole party was lost, and they were sunk in just north of Canada. But this was an amazing party full of science. They discovered the Ross Sea, the Ross Ice Shelf, which we refer to as the barrier because they couldn't get the ship any further south than that. It was 50 meters wall of ice, and Ross Island. And Ross Island, of course, so important to the science now. It's where McMurdo Station is. And an HMS Erebus had its name given to the volcano that's there as well. And this is a wonderful picture. There were no photographs, of course, of this. So, the recordings of it have to be this imaginative, romantic, Victorian assessment of what Erebus and Terra might have been like in Antarctica. This is a Carmichael Water oil painting from the middle of the 19th century. It's complete fantasy, but it is lovely, isn't it? I mean, Antarctica doesn't know anything like this, but it's wondrous just to take a look at what was in the minds of artists at that time. Anyway, let's move on. This is probably more like it. This is what HMS Erebus almost certainly looked like, much better. So this is Antarctica as we know it today, but it always wasn't the case, of course. This is from the Canadian radar sat more than 10 years ago now. But this is what the Antarctic continent would have been looking like maybe a couple of hundred years before that. We really didn't know anything about it. And so in a very short space of human history, we have understood a lot about the surface of the Antarctic continent. We know that it is definitely there. It wasn't always the case. And we've charted its surface really well, but we haven't yet really understood what's underneath the ice, which is the subject of all of this. So a couple of questions. Here we go. Who was the first person to set foot in Antarctica, and when was it? It was 1895. And the history books are divided as to the first person to actually do it. So 1895, barely 100 years ago, even though the Antarctic mainland had not been set foot on. Anyway, the person who is often given the accolade is Norwegian Carsten Borchgrevink. He paid for the expedition to go to Antarctica with the purpose of being first to step foot on the Antarctic continent. But if you asked some New Zealand colleagues, they would offer a different name, and they would offer the name of Alexander von Tonzelmann, who was a ship's hand who was acquired by Carsten Borchgrevink on his way south in Nelson, South Island, and he's not shown on this picture. And the reason he's not shown in this picture is because no one sets foot off a boat, a rowing boat, in this way. There's always someone who has to steady the ship, and that person standing in the water at the front of the ship would have been Alexander von Tonzelmann. So who gets the credit for being the first person to step ashore in Antarctica? Is it the person who paid for the journey, Carsten Borchgrevink, or is it the ship's hand who steadied the ship to allow him to do it, Alexander von Tonzelmann? Well, I'll let you make your mind up. I mention this because that's the first person to step foot in Antarctica, and that's 1895. But it's well worth remembering James Kroll in 1879 did something quite remarkable in his consideration of the Antarctic ice sheet. Now, James Kroll, people I think will know him because of his hypothesis of the causes of ice ages and the way that the Earth rotates around the sun, later updated by Milankovitch in the 1930s. But it was James Kroll who had the initial ideas about orbital forcing of ice ages. But he did many things. And this is a quote taken from David Sugden's review of James Kroll in Antarctic Science in 2014. And it's relevant to today. So this is 6 years before anyone set foot in Antarctica. And this is James Kroll's assessment of Antarctica and what it might mean. So I'll read it out. Antarctic ice sheet melting, would evidently tend to produce an elevation of the sea level on the northern hemisphere in two ways. First, the addition to the sea occasioned by melting of ice off the Antarctic land would tend to rise the general level of the sea. Secondly, the removal of the ice would also tend to shift the Earth's center of gravity to the north of its present position. And as the sea must shift along with the center, a rise of the sea in the northern hemisphere would necessarily take place. Wow, this is 1879, and having these amazing ideas about what Antarctic change might mean globally started really from this and around this point. And I think we all need to take a bit of notice of this. He was also the first person to do any modeling of the Antarctic ice sheet. And he did an assessment, a calculation of what the ice thickness in Antarctica would be. And he had a range somewhere between 3 miles and 28 miles thickness at the center of the ice sheet. Now, bearing in mind we didn't even know that if it was a single continent. In fact, there were discussions around the paper that he shouldn't be publishing this because it hadn't yet been proven that Antarctica was indeed a continent at all. And yet he had this idea that it was a massive ice sheet with a center which was miles thick. Well, he was right about that, and his lower estimate actually is pretty accurate, in fact. And all he needed, funny enough, was one data point to calibrate his model, and he would probably been got much closer. Anyway, a very interesting person who deserves, I think, a lot more credit scientifically than we give him these days. So I want to mention that. Now, the heroic age, the second phase of exploration, is one that people will know about. This is all Captain Scott and things. The first person to seriously think about going to the South Pole was Robert Scott, Edward Mawson, and Ernest Shackleton, three of them together. And they got as far south as 82 degrees, 450 miles from the South Pole. And they were forced to return home because Shackleton got ill. And actually, Scott and Shackleton barely spoke after that. Scott referring to him as too old for exploration, and Shackleton refusing to accept that. They didn't really get on after that point. But the reason it's of interest isn't necessarily because of their failed attempt to get to the South Pole, it's because it was a scientific mission. And the first flight in Antarctica was taken by this party. In fact, the first person to fly in Antarctica was Robert Falcon Scott. This is him in a hot air balloon. And this is the photograph, oh, there we go. And this is the photograph that he took, the first aerial photograph of Antarctica. And you can see the Terra Nova just in the bay in the background. Wonderful, wonderful photograph, indicating that very early on, these exploration missions, these heroic exploration missions, were using technology and to aid scientific discovery, which is something that we still do today. 5 years later, Shackleton, in his Nimrod expedition, got very close to South Pole, 97 miles. They got up the Beerbock Glacier onto the plateau, might possibly got quite close that they could maybe even see the pole in the very distance, but calculated they didn't have enough fuel and supplies to get there and return back. And so they returned back early, just missing their opportunity. And then, of course, the race to the pole in 1911 and 1912, successfully reached by Royal Amazon, 4 companions and 18 dogs. Dogs is important here. And Robert Falcon Scott 30 odd days later, and they perished on the way back. One of the reasons that that's important is because Amazon, he had dogs, and they were great sources of power. And if you wanted, I'm sorry to be to saying this in a rather crude way, but it was happened the case, if you wanted to shoot a dog and eat some of it, you could do that. You could feed the rest of the dog to the other dogs, and you're only down by 1 dog pulling power. So it's a pretty good idea. The British didn't do that. Firstly, they had ponies to pull large bits of equipment, but they were useless. Ponies also can't eat other ponies, and so you need to take pony food with you. And even if you, with the best will in the world, if you shot a pony and wanted to eat it, you couldn't eat a whole pony. And so if you shot a pony, you were left having to pull the carcass, and the home structure, you're hopeless. And then once that had finished, you were left with pulling your sleds and all your supplies yourself, and which was exhausting. But this is taken from the Scott expedition to South Pole, and this is a picture of Edward Wilson. And people often think about the Scott expedition in that horrific way, with those 5 people pictured at South Pole, all very much in danger, and ultimately died and perished. But this is a beautiful picture on the way up the Beerbock Glacier with the sun on their back, and beautifully serene. And people who've ever been to Antarctica will take a look at this. And I know that there are some days in Antarctica which are awful, but there are beautiful days as well, where it gets lovely and warm and serene. And this is actually a beautiful picture. I'd like to talk about Douglas Mawson for a second, an Australian geologist who was the first person to reach the magnetic South Pole during the Nimrod expedition of Shackleton, of course, and had an amazing expedition, the Australian Antarctic expedition, to chart around about 1,000 kilometers of coastline in East Antarctica, where 2 of his colleagues died, and he managed to make it back. This is Camp Dennison, the windiest place on Earth. Winds can reach up to 200 miles an hour at the edge of the East Antarctic ice sheet by a katabatic wind that funnels through the glacier that's there. Well, you might wonder why on earth you put a station in that place. They didn't want to. It was simply the last opportunity they had. The ship that they were sailing in had enough coal to only go so far and go back to New Zealand. And the ship's captain said, well, listen, we can take you here, or we're going back home. So it's either here or back to New Zealand. And they said, oh, well, this is Australia, big pun. They said, well, this is it. We'll go here. Camp Dennison it was. And it wasn't a particularly good choice, but nonetheless, an amazing feat of endurance, nonetheless. And of course, Ernest Shackleton, this is, people know about this, the idea going from South Georgia, getting the idea of Shackleton's expedition is people had already been to the South Pole. This was all about crossing the Antarctic continent. He was going to do that with his team. And of course, they got beset in sea ice, pushed further north, ended up on Elephant Island. No one knew they were there. Everyone thought they were either the other side of the continent, and if they weren't the other side of the continent, they were dead. No one expected them to be at Elephant Island, and so they realized they were going to perish unless they got help. And so they got one of the lifeboats, the James Caird, and they launched it and got back to South Georgia, a few of them at least. It was, again, an amazing, amazing story. This is all heroic stuff. There's lots of science that was done, but it really involved, a lot of it involved this type of activity, which was pulling your equipment by yourself. Now, it seems a bit hazardous. Actually, there was quite a science behind it. There were a lot of calculations that were done about what equipment you were using, the weight that could be done per person. And so it wasn't a sort of haphazard and amateur, but nonetheless, it was still very exhausting to do that. So the First World War happened, and then afterwards, people got back. The first person to take a flight in Antarctica was 1928, and this is Hubert Wilkins, an Australian. And he had this aircraft that can land underwater, and they took it to Antarctica, assembled it there, and they flew for a couple of minutes around an island. It was a very short flight, but it proved the point that you can use this emerging technology, emerging flight technology, to cover large distances in Antarctica. This is 1928. A year later, the next year, Admiral Richard E. Byrd was flying from the Little America camp to the South Pole, didn't land there, and got back again just 1 year later. The rate of change of exploration in Antarctica is enormous at this time, and it's benefiting from this rapid rise in technological advances. And it goes hand in hand, this idea of scientific discovery and the use of technology is something that we still do today, of course, but really starting at this point. 6 years later, the first trans-Antarctic crossing by Lincoln Ellsworth, and discovering so many things on that journey, heading for the unknown, bold and rugged mountain peaks across our route lay ahead, some of which seemed to rise almost sheer to 12,000 feet, as far as the eye could see, and then the range, the eternity range, and some mountain range that we know a lot about these days. And this was Admiral Byrd's map of Antarctica before the Second World War. And you can see the general outline of Antarctica is not so good really, but at least we know it's there. We don't know if it's one continent or not. There are some bits we know a lot about, especially around the Ross Sea. But there are many parts of Antarctica that's completely unexplored, and we don't know much about it at all. And that's the state of knowledge as we enter the Second World War. Following the Second World War, with all the amazing technological advances that were taking place around that time, people got very enthusiastic about polar exploration again. And barely 10 years after the world was at war, there was something called the International Polar Year, and International Geophysical Year as well, which had a real center on understanding the Antarctic continent. As part, there was an international campaign. There were lots of countries involved, but primarily, and in particular, the US and the Russians, the Soviet Union at the time, were interested in exploring Antarctica. And well, I've told you who was Ronald Amundsen was the first person to get the South Pole, followed afterwards by Captain Scott and his party, but who was the next person to get the South Pole? You know, it's a good question to ask. Who was the next person? Well, it was a US person, and it was Rear Admiral George Dufek. As part of the US plans for the IPY, a permanent station at South Pole was being proposed. But of course, what had to happen was, we don't want to do what Captain Scott on North Amazon did. We actually probably want to use aircraft to get there, and that'll be a much more efficient way of doing it. So can you land an aircraft at South Pole was the mission that they had. This is the Pacer RSR with pipes, warm air pipes going in to keep all these engines nice and warm. Very good. And this is George Dufek at South Pole. So this is a picture back at South Pole many years after Captain Scott had left it. This is the next person to get to South Pole. Now, you see they've got a cine camera over here. That was useless. They kept the humidity in the aircraft a bit too high, probably unwittingly, obviously. But when they got onto the ice, temperature must have been about -25, -30, something like that, and all the equipment froze up. So the film just didn't work at all. A couple of snapshots like this one, and after just 20 minutes or so of being on the ice, everyone's getting frostbitten. So he let out these immortal words. His words, not mine. Let's get the hell out of here, is what he said, and they got back into the plane. Now, there were two planes that went to this journey, because if something went wrong, there needed to be another plane as a backup to get them back out again. And something did go wrong. This plane couldn't take off. It was stuck in the ice. But on either side of the main body of the aircraft were rocket boosters. And so they let off a couple of rocket boosters to free the ice, and free the plane out of the ice, but it didn't work. So they let them all off at once to see if they could shift it, and it did work. But this is the aerial photograph of that other plane seeing this DC-3 take off. This is a DC-3, by the way, to take a notice of that too. And this is then back at McMurdo Station, and having successfully got to, landed, taken off, and back from South Pole in just a few hours. Amazing. The International Geophysical Year was a wonderful, wonderful thing. I mean, we were at war with each other barely 10 years before that, you know, the worst of humanity. And yet the best of humanity happened in science shortly afterwards. We realized we didn't really understand the world that we were living in. And the IPCC wanted to observe geophysical phenomena and to secure data from all parts of the world, to conduct this on a coordinated basis by fields and in space and time, so that results could be collated in a meaningful manner. It's a wonderful quote, and it's something that resonates today, of course, in science. This is Charlie Bentley from the University of Wisconsin, trekking across the West Antarctic ice sheet. He didn't know if the Antarctic continent was one, or it was divided into two, and one of the things that Charles Bentley wanted to do was understand that. And you can see this is a wonderful picture of a tractor train undertaking. It's got a forward-looking radar to detect crevasses, but essentially this is doing seismic exploration and setting off a charge and seeing what happens. The idea behind seismic exploration is you've got to drill two holes, and you need to drill two holes into the ice, because the surface snow will essentially absorb the sound waves that come off the explosion. So you drill into the hard glacier ice, one, to set the charge off, and two, to record the reflections, the sound reflections that come off the bed. And it'll take about, 50 meters or so you've got to drill into the ice. So it's going to take a good day to get your experiment set up. And then you set off your charge, and then you've got your nice seismic reflection experiment. You know that the two-way travel time of sound you know the velocity of sound in the ice. You know that you can record the two-way travel time, so you can work out what the ice thickness is, and that's what they did. And then you pack it all up on your tractor train. You move it another some kilometers, 10, 20 kilometers, and you do it again. But essentially, one data point, you're going to be collecting one data point every sort of 2 or 3 days. That's about what you're going to be doing. And it's brilliant data. It gives you an amazing, accurate depiction of the ice thickness. And if you can do that over a season, you can get a pretty good transect of the West Antarctic ice sheet. And that's what Charlie Bentley and his colleagues did, proving really that that part of Antarctica was all connected and was very deep and was below sea level, and some amazing discoveries were made. But this is the person that really advanced scientific discovery in Antarctica. This is Gordon Robin, who at the time was an Australian physicist, director of the Scott Pell Research Institute in Cambridge for many years. And in his obituary, it sums up his contribution very, very well. This is written by David Drury, who was another director of SPY and also the British Antarctic Survey. One of his most inspired decisions was to advance the charting of glacier and ice cap thickness by airborne radio echo sounding rather than explosions conducted at the surface. The point being, you can let off your radio waves penetrate straight through cold ice, but they reflect where there's a change in the dielectric properties of that substance. And there is, of course, at the bed of the ice sheets, whether it's rock or sediment or water. And just like seismic exploration, you can record the two-way travel time, you know the velocity of the radio wave in the ice, and you can record the ice thickness. But rather than one measurement per 2 or 3 days, you can record many per second. They increase the rate of data acquisition overnight by more than 5 orders of magnitude in doing this, and completely revolutionized our ability to measure the continent of Antarctica in the 1960s and 1970s. This is Gordon in, again, in McMurdo Station. Amazing international collaboration of the United Kingdom, United States, and the Technical University of Denmark as These are the radar antennas on a Hercules C-130 aircraft. To keep a memory of these antennas, because they might come back in a second. And this is what the radar data look like. This is from Ridge B in East Antarctica, a beautiful mountain range and a valley in between. Wonderful, very, very similar to radar data that we collect today. And this is what he did. This is Gordon Robin and his team essentially charting somewhere around 40% of the continent of Antarctica over just 3 seasons. It was an amazing piece of discovery. You might wonder why he just didn't continue and survey the whole lot. Well, in 1979, there was a big air disaster. A tourist plane, a DC-10, I think it was, unfortunately crashed into Mount Erebus, killing everybody on board. And there was a lot of things happening at that time. And essentially, long-range aircraft deployment with radio echo sounding on board was stopped and didn't return for some time, in fact. Based on the SPY NSF TUD data, in 1983, this is the depiction of the landscape beneath the ice in Antarctica. And you can see there are some bits which are quite well detailed, the Cycle Coast over here, the blues being the bed of the ice sheet well below sea level, thanks to Charlie Bentley as well, but many other of the radio echo sounding data, the Ellsworth Mountains over here and the subglacial highlands. We've got some really good detail over here. And of course, around Dome Sea, the Aurora Basin, Wilkes Basin, pretty good idea about it. But look over here, that's large parts of East Antarctica with basically no data at all. This is just 1983, 40 years ago. By 2001, the first bed map depiction of bed topography was produced, and there was an improvement over the folio map in 1983, but it hadn't changed an awful lot. There were still these broad regions where we didn't know too much about things. By 2013, more data had been acquired, and we'd improved things a lot. I mean, the resolution between these, you can toggle between the two, is quite substantial, actually. And this is, of course, a major input to numerical ice sheet models. We're trying to understand how the Antarctic ice sheet is changing using a model that has this as a bed elevation isn't particularly good. Using a model that has this as its bed elevation is slightly better, but could be improved, and getting better still if we use this model. But there are still places of the Antarctic margin and places around the recovery system over here and the Princess Elizabeth Land over here where we haven't got much data. So some of us over the last decade or so have been trying to fill those data gaps. This is another DC-3. It's now called a Basler BT-76, but it's the same type of aircraft that George Dufett used to get to South Pole. Those radar antennas are the same type of radar antennas that Gordon Robin was using on that CL-130 Hercules transporter aircraft. So there's nothing new in Antarctic science here, but it seems. And this has been an amazing collaboration that I've been involved in with the University of Texas at Austin, with French, the Australians, and actually with Chinese program as well. That's been trying to fill in a lot of these data gaps and to understand scientifically what's going on, both historically in Antarctica and of course into the future. So this is what things were like in 2013. And since then, we've been having this wonderful new aircraft purchased by the Chinese Antarctic program and flying across parts of Antarctica, the last remaining large unexplored regions of the Antarctic continent. You know, this is something that started with Captain Cook in the 18th century, and is only just really at the first order level being filled by the Chinese program. But this is what BEDMAP 3 is going to look like. This is the data coverage that's going into BEDMAP 3, which is being put together right now. And the data set that this can produce is going to look something like this. This is actually Morlingham's bed machine product, but with the inclusion of new data from around Princess Elizabeth Land over here. So it's not quite the bed machine product that was published, it's an update to it. And BEDMAP 3, which is being compiled and assembled on behalf of the international community, but by the British Antarctic Survey, is going on right now. And this really will be the first time we've got a full assessment to the first degree of the subglacial topography in Antarctica. So that's what we've been trying to do. It has a very rich historical lineage going back to all those things that I mentioned. And as I said, I think it's quite important when we're thinking about sea level rise, when we think about the science that is important to us, we understand where this science has come from. We're trying to, obviously, with this information, trying to nail this first one, mapping the subglacial topography and ice cover bathymetry of Antarctica, but also to understand that models of the Antarctic ice sheet are pretty good, but they could be better, especially if they incorporate as much information from the geophysical data as they possibly could. And that's something that's driving me and many others to advance next generation ice sheet models and to recouple the glaciological community, some of which are doing geophysics, some of which are doing numerical modeling. Some years ago, maybe 30 years ago, there were people doing both. I think we need more people doing both of these things. And if we were to do that, it might well help us to reduce uncertainty in future sea level change, because as I said, as you know, Antarctic ice sheet is changing, and it's changing in line with the worst case scenario, and that's likely to continue. And we need to get ourselves as scientists better equipped to be able to understand and predict how Antarctica is going to change in our world and in our future. Thank you very much, and I'm very happy to answer some questions. Thank you.
Thank you very much, Martin. That was a fascinating talk and a really nice addition to the series. Oh, we've got questions coming in on the chat. I might pick on people. I hope you don't mind. So a while ago, we had a comment from Stephen Griffiths, which I didn't mention because I didn't want to break up the talk. But he makes the argument. There's some evidence that it goes back to when you were talking about the first people who stepped on Antarctica, and there is some evidence that perhaps that the Maori, I think the natives of New Zealand, might have visited Antarctica very early on in the 7th century or something.
You know what? I didn't know that. Thank you. I'm going to add that to my talk. Whenever I do a talk like this, it's surprising how much comes out, and I don't know much at all, right? And who does? But it's always good to understand this. Thank you ever so much. That's a really, really interesting suggestion. I'm going to read that with a lot of interest. Thank you.
Did you want to say something, Stephen? I noticed you.
Yeah, I just noticed it, and EOS just had a pointer to it, and there was a paper in April of 2021 in a New Zealand journal that I put a link to the HTTP, the address in the chat. You know, I think it's all oral history. I'm not sure if there's any evidence from archaeological, but it's probably worth following up and seeing.
Yeah, thank you. I mean, there was a debate, of course, who was the first person to set foot in Antarctica and the first documented.
Yeah.
But was the first, what I said, that actually there was some unconfirmed report that it happened, 60 or so years earlier than that, but it was unconfirmed. But anyway, between then and the later 19th century, there was nothing. It's bizarre, but I would take a look at that paper. Thank you ever so much. It's really interesting. Thank you.
Thanks, Stephen. We have a question from Alice. Can I pick on you and ask you if you want to unmute and say hi and ask a question?
Now, I was just wondering if you're using any like satellite data from NASA or anything like that.
Well, I mean, satellite data has been revolutionary for us, of course, to understand from our altimetry perspective, to understand the changes that are going on in Antarctica. That's not what I use personally. It was mostly airborne and ground-based work, ground-based data that I'm using. It's very difficult to do an ice-penetrating radar system on a satellite for a number of reasons, but no, it's airborne. And I think really the future of airborne geophysics is probably over the coming decades. It's not going to be flying DC-3s around Antarctica. I doubt. It'll be more autonomous aircraft and drones and things like that, which can fly for much longer times, which don't have to have half their weight to keep people on board alive. They can just fly for much longer, high altitudes, and just get much more information done. You know, I showed you that. I'm going to put it up again. That picture of. Here we go. This one here. This is what we understand about. Oh, can you see that? Okay. Sorry, you got that. Yeah, I did. Put it back.
Yes, that one. That's the one that made me wonder.
yeah. I'm going to go back. Sorry.
You could use like another layer of satellite data or something.
Well, this is it. Like, this is so. Is this impressive? Right. This is all the information we have about subglacial Antarctica, and even then there were gaps. You know, between transects, there are no massive gaps anymore, but there were still lots of gaps. And some of these data, stuff over here in the middle of East Antarctica, you know, it's 40 or 50 years old. So we're still relying on a lot of stuff. But my take with this is that this looks like a patchwork quilt of bits and bobs of data collected from various surveys over various years, stitched together. And that's because it's exactly what it is, right? You would not, if you wanted to explore subglacial Antarctica and get a topographic map that's useful for ice sheet models to better reduce uncertainties on sea level, you would not produce this idea. You'd have you'd have data collected parallel to and orthogonal to flow lines. You work out exactly where the drainage basins are. You do it in a completely different idea. And I was speaking to colleagues about this. I said, this is going to look like a laughable attempt at a depiction of subglacial Antarctica in about 50 years' time. It needs to be, actually, if we're going to advance the science. What we're going to see is a much more carefully coordinated and an acquired survey of the Antarctic continent, if we're really going to help to understand what sea level is going to be like in this century. And similarly for Greenland ice sheet as well, I should think. So, but understand that, you know, I'm not being critical because, you know, I've been involved in a lot of these projects myself. It's just that this has been arrived at in a kind of happenstance way. And we just have to appreciate that scientifically, this has not been designed for the purpose that we need it to do. So I didn't really answer your question.
Satellite data, like to see where it correlated with some of this.
Yeah, well,
fill in the unknown areas. It's just a question. I don't know.
Well, we have the altimetry, and we can pretty much work out, because we know in the first order what the bed is like, that the bits of the Antarctic ice sheet that are changing the most is where we would ordinarily be most concerned about, because it's where the ice is resting on a bed well below sea level.
Yeah.
And in a gross sense, we understand that, and that's kind of fundamental knowledge. But to really understand the interaction between the ice and the ocean and the atmosphere, we need much finer detail in this information than we have at the moment, and that's missing. So, you know, we do need to concentrate on resolution in the parts of the Antarctic continent where we really most need it, and that's at the margin. This information gives us a really good way to understand where it's needed, where we need to go to, what work we now need to do. But most of that work is now ahead of us.
Thank you.
Yeah. We have a question from Roger, or Roger has his hand up. We'd like to. Yeah, thanks very much.
Yeah, hi. Can you hear me? Cool. Thanks for your wonderful talk and for your contributions over the last many years. I hadn't ever heard of James Kroll, but it sure seems like some of James Kroll's ideas were forerunners of the GIA modeling community. So I wondered what impact Kroll had on later literature. Well, like, was he known, talked about?
No, he wasn't. I don't think and that's part of the reason I like to bring him up in discussions like this, because he was an amazing self-taught scientist. He was a janitor in a Glaswegian museum, Scottish. Rose to become a fellow of the Royal Society. Amazing. Had these amazing ideas generally about science and glaciation and things, and yet his big theory about the orbital causes of ice ages was first adopted, but then disputed, and he died with people not really accepting his ideas at all. So he was a sort of a person who rose. He had a sort of rise and fall in his credentials, and died when it was, unfortunately, when it was quite a low point. Very similar to Miloslav Milankovic as well, who also died without people really believing him. It was only the seafloor sediments and the ice cores that did them both. But I do think we need to go back and to recognise that there were some people who had these really original ideas. I mean, I talk about original ideas in science, and some people do. I'm not sure that I have. You know, a lot of it is sort of iterative and you know, going back over what other people knew and just filling some gaps and helping. But original ideas, you know, they're rare, right? And you know, there were some people who had them in abundance. It seemed it was an amazing time for scientific discovery. But yeah, check him out. David Sugden did a lovely paper on him in 2014. It's a really good read.
Next up, we have a question from Ralph. Ralph, would you like to say hi? They might be struggling to unmute or I'll read it out. Okay, so this is from Ralph Kahn. Thanks for a wonderful historical perspective. Just wondering, what role does the project Icebridge and, for example, ISAT objectives might have played in this history?
Yes, absolutely. Very good. So, I mean, ISAT, just like Cryosat and EOS 1 and 2 beforehand, depicting altimetric changes of the Antarctic ice sheet with increasing precision, just extremely important baseline knowledge of change that's going on in Antarctica and Greenland, of course, and the sea ice. So yeah, that is, I mean, fundamental is often used a lot, but I think it's very appropriate in the case of ISAT. Operation Icebridge, spanning between ISAT and ISAT 2, but using airborne work and laser altimeters on board aircraft is also really important. And radio echo sounding has benefited massively from that, because if you're going to fly an aircraft around parts of Antarctica, flying over ISAT transects, as was the case, you might as well equip that aircraft with lots of the full geophysical payload and get as much information as you possibly can. And that's exactly what happens, of course, you know, with airborne radio echo sounding and gravity and magnetics, and as much information as you possibly can get to maximize the scientific return. And that has been done. So the release of funding through the Icebridge program, coupled with existing programs that were taking place, like the IceCap program, and others as well, has been a very, very useful combination, and has allowed us to really advance knowledge of subglacial Antarctica at a rate probably not seen since the 1970s. I mean, the advance, BedMap 3 will look pretty different to BedMap 2, and that's as a consequence of all that stuff that has come out. So, you know, we've really done a pretty good job of filling those data gaps. But as I said, you know, the next step is to understand what we now need to do to improve the bed depiction underneath the Antarctic ice sheet in a way that numerical models will find most useful, and that we haven't yet done that. but thank you. Yeah, Icebridge and ICET2 have amazing contributions.
We have a question from Neil asking where are the drones? Where are the small radar systems on drones?
They're being developed. Yeah, absolutely, they are being developed, and it's tricky. And there's and I know of several teams that are doing this sort of thing. I mean, it's difficult at the moment. Only field work in Antarctica is challenging at the moment, but there are plans to deploy drones either from the ice edge or from ships as they're sailing around Antarctica and catch them in nets. And I know that is happening as planning to be happening as well. And it depends what you want to do. You know, if you want to understand the marginal changes or take a good look at the state of health of ice shelves, then drones launched from ships is probably a good idea. If it's the sort of tectonic evolution of the Antarctic continent itself and the lithosphere, you're going to need to deploy on the ice and in the center. And again, that's going to be very different. They're coming. My suspicion is it will take. I mean, I had a good chat with Peter Barrett some years ago, famous Norwegian geologist who offered advice that it takes 10 years to do anything significant in Antarctica. That's probably wishful thinking as well. Having your idea, and then all the hurdles that you have to do in terms of raising the funding for it, which is not insignificant, of course, getting the equipment that you need to do. And after you've done that, which is, if you've been able to do that, you're only at the start. Then you've got to assemble all the logistics, you've got to put it in place. And once you've done all that, you can finally do the experiment. But it takes an awful lot of work. Unlike many other areas of science, doing Antarctic science takes a long time. It's very complicated. That when there are other areas of science, I mean, space science almost certainly like that as well. But Antarctic science and the long lead times to any advances are substantial, which is remarkable, isn't it? When you consider that sometimes in our history, scientific advances in Antarctica happen quite quickly, but they happen quickly as after that 10 plus years of planning and getting on with things, which is absolutely necessary.
We have a question from Gavin Schmidt in the chat, or a point about Kroll, I think. Gavin, would you like to, any chance you want to unmute? Not really, he says. He doesn't want to. Okay, fair enough.
No, it's a very good point. And you know, James Kroll absolutely had an influence on Milankovitch. Actually, David Sugden, again, who's looked into this, explains that Kroll would have got his calculations right, but he made a sort of fundamental error in assuming that glaciations happen as a consequence of cold winters, and bases all his calculations around that. And of course, as we know, in glaciology, it's cold summers that causes glaciers and ice sheets to grow, not cold winters. And if it had made that change, that knowledge, if he had that knowledge, he might have got his calculations a bit better. But actually, Milankovitch's analysis, very heavily based on Kroll's, got that aspect of glaciology right and came up with some, well, his calculations were completely spot on, of course.
Do we have any further questions, perhaps final comments from everyone? A huge thank you again, Martin, for speaking today. It was really wonderful. We're coming up on about noon, which is typically when we would close off and let people go to other meetings or what have you. Do we have any final questions or points from the group?
Well, a point for me, Craig, just to say thank you ever so much. It's really a pleasure to speak to you all, and I appreciate the nice comments and things. If anyone has any questions they want to ask me offline, just send me an email. I'm very happy to respond to things. But like I said, I think all of us need to take a look into the history of the science that we are doing to see how it's possible that we can do so much. And you know, let's not forget them.
Thank you very much. That was a great ending. Thanks, everyone. Hopefully we'll see you next week, and I hope you have a great rest of the day.